Can you imagine a world where problems that take years to solve with our current computers are solved within seconds? We live in an era where the hum of servers and the glow of screens are as ubiquitous as the air we breathe. From the smartphones in our pockets to the supercomputers that predict our weather, classical computers have woven themselves into the very fabric of our lives. They've transformed how we work, play, and communicate, and they've unlocked new frontiers in every field imaginable. Yet for all their brilliance, classical computers have their limitations. They struggle with complexity and they stumble over large data sets. Each bit in a traditional computer can be either a 0 or a 1. This binary system, although effective for many tasks, is not sufficient for handling the massive amounts of information we're generating. So, as our world becomes more data-driven, our need for computational power only escalates. Consider the convoluted problems of cryptography or the intricate puzzles of molecular simulation. These are problems so complex that even our most powerful supercomputers need years, if not decades, to unravel them. It's like trying to catch the wind with a net or map the stars with a magnifying glass. The tools we have are simply not enough. But what if we could process more than just ones and zeros? What if we could perform multiple calculations simultaneously rather than sequentially? What if we could harness the strange, almost magical properties of quantum mechanics to leapfrog the limitations of classical computing? This is more than just a dream. It's a revolution that's already happening. It's a shift from the binary to the quantum, from the predictable to the uncertain, from the known to the unknown. It's a journey into a world where the rules of physics as we know them are turned on their heads. To transcend these limitations, a new form of computing is emerging: quantum computing. So what exactly is quantum computing? Picture yourself flipping a coin. It's either going to be heads or tails, right? Well, in the quantum world, it can be both. This is due to a concept known as superposition. Unlike classical bits, which can be either 0 or 1 quantum bits or qubits, can exist in a state where they are both 0 and 1 at the same time. Imagine having a magical coin that, while flipping, instead of being heads or tails, it's both simultaneously. It's only when the coin lands and we take a look at it that it chooses to be one or the other. This is the magic of quantum mechanics and how qubits work in a nutshell. Now, let's dive a bit deeper into these quantum bits, or qubits. In the world of classic computing, everything is binary. That means the smallest piece of data, a bit, can either be a 1 or a 0. This binary system is the backbone of all current computing systems. It's a language that computers understand, and it's how they process information. On the other hand, quantum computing uses qubits. These qubits, thanks to the quirky laws of quantum mechanics, can be in a state of superposition, meaning they can be both a 1 and a 0 at the same time. This potentially allows quantum computers to process a massive amount of information simultaneously. Moreover, qubits can also be entangled. This means the state of one qubit can be dependent on the state of another, no matter how far apart they are. This extraordinary phenomenon allows quantum computers to perform complex calculations at a speed that's currently unfathomable with classical computers. In essence, quantum computing holds the potential to process information in ways that are currently unimaginable with classical computers. It's like stepping into a new dimension of computing, where the rules we've been accustomed to no longer apply. Quantum computing isn't just a new way of processing data, it's a whole new way of understanding information. But what makes quantum computing so powerful? Well, let's dive into the heart of it. The magic, if you will, of quantum computing lies in two fundamental principles of quantum mechanics: superposition and entanglement. Let's start with superposition. In the classical computing world, data is stored in binary bits, which are either a 0 or a 1. However, in the quantum realm, we have something called a qubit. A qubit, thanks to the principle of superposition, can exist in a state that is simultaneously 0 and 1. Yes, you heard it right, simultaneously. So if you have 2 qubits, you have 4 possible states, and with 3 qubits, you have 8 possible states, and so on. This exponential growth means that a quantum computer with 100 qubits can process 1,000,000 trillion pieces of information at once. That's a 1 with 30 zeros behind it. Now let's move on to entanglement. This is a phenomenon where 2 qubits become intertwined, such that the state of one qubit is directly related to the state of the other, no matter the distance between them. This connection allows qubits that are far apart to interact with each other instantly. Imagine being able to toss a coin in New York and causing a coin in London to land the same way instantly. That's the level of interconnection we're talking about. These principles allow quantum computers to process massive amounts of data simultaneously, solving problems in seconds that would take classical computers thousands of years to crack. They hold the potential to revolutionize industries, from healthcare to finance, by making computations that were once thought impossible, possible. This power, however, brings along its own set of challenges. But that, my friends, is a topic for our next scene. Stay tuned as we delve into the hurdles and complexities that come with harnessing the power of quantum computing. What are the hurdles that stand in the way of quantum computing? Just like any other technological advancement, quantum computing faces its fair share of challenges. Before we dive into the details, it's important to acknowledge that these challenges are not showstoppers, but rather speed bumps on the road to quantum supremacy. Firstly, there's the issue of qubit stability, also known as quantum decoherence. Quantum bits, or qubits, are the basic units of information in quantum computing. Unlike traditional bits that can be either 0 or 1, qubits can be both at the same time. However, maintaining this state is not a walk in the park. Qubits are extremely sensitive to their environment, and even the slightest change can cause them to lose their quantum properties. This instability makes it difficult to perform complex calculations and limits the time during which computations can be made. Next on the list is error correction. The fragile nature of qubits means they're prone to errors, much more so than classical bits. To get reliable results from a quantum computer, we need to correct these errors. But here's the catch. Traditional error correction methods don't work with quantum information. Developing new, quantum-friendly error correction algorithms is a massive challenge that researchers are still grappling with. Lastly, let's talk about the elephant in the room: cost and complexity. Building a quantum computer is not just about putting together some fancy hardware. It requires creating an environment where quantum effects can be carefully controlled. This involves cooling the system to near absolute zero temperatures and isolating it from all forms of interference. As you can imagine, this doesn't come cheap. The sheer complexity of building and maintaining a quantum computer is a significant hurdle. Despite these challenges, the potential applications of quantum computing are immense. These obstacles are not insurmountable. With each passing day, we're inching closer to a future where quantum computers could redefine the boundaries of computation. Where can we apply the power of quantum computing? Let's dive into the potential applications of this burgeoning technology across various fields. First off, we have cryptography. Today, we use complex algorithms to keep our digital lives secure. Quantum computing, with its ability to solve problems exponentially faster than classical computers, poses a threat to current encryption methods. However, it also provides a solution. Quantum cryptography offers a way to create virtually unbreakable codes, ensuring our digital information remains secure in the quantum age. Next, let's look at medicine. Quantum computing could revolutionize drug discovery and disease modeling. By simulating the behavior of molecules, quantum computers could help researchers design new drugs or predict the spread of diseases, potentially saving millions of lives. In logistics, quantum algorithms could optimize routes for deliveries or reduce traffic congestion, making our cities more efficient. Imagine a world where your packages always arrive on time and your commute is never delayed by traffic. That's the promise of quantum computing and logistics. Then we have climate modeling. Predicting the Earth's climate is an immensely complex task. Quantum computers, with their ability to process vast amounts of data, could provide more accurate climate predictions. This could help us understand the impacts of climate change and devise strategies to mitigate them. In the financial sector, quantum computing could transform financial modeling, risk assessment, and trading strategies. By processing complex financial data at unprecedented speeds, quantum computers could help investors make more informed decisions and potentially increase their returns. Lastly, quantum computing could even help us understand the very fabric of the universe. By simulating quantum phenomena, scientists could unlock the mysteries of quantum mechanics, potentially leading to groundbreaking discoveries in physics. These applications only scratch the surface of what quantum computing could possibly revolutionize. The potential of quantum computing is immense, and as the technology matures, we can expect to see its impact across even more sectors. So let's keep an eye on the quantum horizon. The future is bound to be exciting. What does the future hold for quantum computing? Well, the answer lies in the relentless pursuit of scientific advancement. as researchers, academics, and tech visionaries continue to unravel the potential of this radical technology. The future of quantum computing is bright, shimmering with possibilities yet to be discovered and harnessed. In the race to build the world's first fully functional commercial quantum computer, major tech companies are investing heavily. Giants like Google, IBM, and Microsoft are not just spectators in this thrilling race. They're the pace setters, driving innovation with their cutting-edge research and development. But it's not just the big players. A multitude of startups are also making significant strides in the field. From creating quantum algorithms to developing quantum software platforms, these budding ventures are pushing the boundaries, redefining what's possible, and paving the way for a quantum revolution. The future of quantum computing is also nestled in the halls of academia. Universities and research institutes around the world are fostering a new generation of quantum physicists and computer scientists. These bright minds are not only learning about quantum mechanics, but also contributing to its growth, adding fresh perspectives and novel approaches to the mix. Moreover, international collaborations are playing a pivotal role. Quantum projects are increasingly becoming a global endeavor, transcending geographical borders and cultural differences. This spirit of cooperation is accelerating the pace of quantum development, fostering a sense of unity and shared purpose among researchers. Even governments are recognizing the importance of quantum technology. They're allocating substantial funds for quantum research, understanding that the countries leading in quantum computing today will be the superpowers of tomorrow. So what does the future hold for quantum computing? It's a future of discovery, innovation, and collaboration. A future where quantum computers could revolutionize industries, from finance to healthcare, from logistics to cybersecurity. A future where the enigma of quantum mechanics is not just understood, but harnessed for the betterment of mankind. The era of quantum computing is no longer a distant dream, but an imminent reality. So, are we ready for this quantum leap? We've journeyed through the current state of computing and unveiled the enigma that is quantum computing. We've witnessed its immense power, a force that could dwarf our current computing capabilities. Yet, we've also seen the hurdles that stand in its path, the challenges that must be tackled for us to harness this power effectively. Quantum computing holds the potential to revolutionize myriad aspects of our lives, from healthcare to finance to climate modeling. It could transform industries, making the impossible possible and the unimaginable a reality. But to reach this quantum future, we must first overcome the intricate difficulties that quantum computing presents. We stand at the precipice of a new era, an era shaped by quantum computing, where its potential to revolutionize industries is only matched by the challenges it presents. As we stand on the brink of this technological revolution, one thing is certain: the quantum future is going to be nothing short of extraordinary.